You know how sometimes you look at something and you just know what it is? A ball is a ball. A wave is a wave. Simple, right? But what if the very building blocks of our universe don't play by those simple rules? What if they're both a ball and a wave all at once? That's not just a mind bender. It's a cornerstone of reality.
It absolutely is. Yeah, at the smallest scales, our everyday classical definitions really break down. Today, we're diving deep into one of the most foundational and frankly mind-bending concepts in physics, wave-particle duality.
Okay, so our mission for this deep dive is to unpack this idea, trace its challenging journey through scientific discovery, and then embark on an even wilder philosophical leap. We're talking about a framework that redefines duality, culminating in a truly visionary concept, the quantum topological speculative decoder.
Mm,
We're moving from the absolute basics of quantum entities right through to, well, cutting-edge ideas that could shape the future of quantum technology.
exactly. We'll start with the foundational scientific explanations of wave-particle duality, and then we'll introduce a fascinating dialectical framework. This isn't just abstract thought. It's, a way of thinking that connects philosophical insights with deep mathematical and physical intuition, pushing the very boundaries of how we understand the discrete and the continuous in nature. Get ready for some genuine aha moments because this journey, it really recontextualizes everything.
Okay, let's unpack this foundational puzzle then. For centuries, brilliant minds wrestled with the fundamental nature of light. Was it made of tiny, distinct particles like miniature bullets? Or was it an ethereal ripple, a wave spreading through space, like ripples on a pond?
Precisely. And while that debate raged for, well, centuries, experiments eventually forced scientists to accept something astonishing.
Light showed characteristics of both. Take the photoelectric effect, for instance. When light hits certain metals, it can knock electrons loose,
Hmm.
but only if the light's frequency is above a certain threshold,
Right.
regardless of its brightness. This showed that light arrives in discrete packets of energy, what we call photons, acting very much like individual particles, like they had enough punch to eject an electron.
Right. Particle-like punch. But then you have something like Young's double slit experiment. If you shine light through two tiny slits, instead of just two bright lines on the screen behind, you get this beautiful, intricate pattern of bright and dark fringes. That's exactly what happens when water waves interfere, right? They add up or cancel out. So light doesn't just act like a particle, it demonstrates classic wave-like diffraction and interference. It's got this undeniable dual nature. And this duality isn't exclusive to light. That's the kicker. Initially, electrons were considered purely particles. You can track them, see them flash individually on a screen in, say, a cathode ray tube. But then, thanks to insights like the de Broglie relation, which suggested that all matter has wave-like properties, subsequent experiments actually showed electrons also exhibit wave-like behavior. They, too, can diffract and interfere, creating those same patterns as light in a double-slit experiment. It's amazing.
So, okay, what does this tell us? What are the big takeaways from this baffling discovery? First, these quantum entities truly possess characteristics of both waves and particles, and they do so simultaneously.
Simultaneously, yes. It's not like they switch back and forth depending on their mood.
And second, what we actually observe depends entirely on how we set up our experiment.
Completely. A quantum entity seems to behave like a wave when it's propagating, sort of exploring all possibilities, but like a distinct localized particle when we try to interact with it or, measure it.
And third, our classical, everyday concepts of wave and particle.
Mm.
They're just insufficient. They don't really capture the full picture.
They really don't. They're useful analogies from our world, but the quantum reality is something else entirely. This wave-particle duality is not just some abstract oddity, it's a cornerstone of quantum mechanics, absolutely essential for explaining how matter and energy behave at the atomic and subatomic levels. And understanding it wasn't just a theoretical breakthrough, it led directly to the development of technologies you use every single day, things like lasers, transistors, and advanced medical imaging devices like MRIs. It absolutely forces us to move beyond our classical understanding of physics.
Okay, here's where it gets truly fascinating for me. If we accept this dual nature, how do we even begin to, wrap our heads around something that is both a wave and a particle?
Mm.
What if this isn't just a paradox we had to live with, but actually a window into a deeper, more fundamental type of relationship?
This raises a profoundly important question, yeah. One compelling framework suggests we stop viewing this as just a paradox and instead see it through the lens of a dialectical structure.
A dialectical structure. What does that mean exactly?
It's a way of understanding reality through the tension and interplay of opposing concepts in this particular case, the discrete versus the continuous. And, this isn't just some abstract academic exercise. For me, this way of thinking really crystallized after years of grappling with these kinds of dualities. I used to lean towards monism, the idea that everything ultimately resolved to one fundamental substance or principle. But then, through a lot of personal reflection, I started tunneling through my own experience of duality, not just in physics, but in everyday dichotomies like, say, order and chaos, or individual freedom versus collective responsibility. I realized that the richest truths and most dynamic systems often emerge from the tension between two seemingly opposing poles rather than just one. This shift from monism to dialectics, it changed how I looked at everything, including quantum physics.
That's a really interesting insight. Like, seeing the whole picture isn't just one color, but maybe a canvas of two powerful interacting ones. So, when we talk about the continuous in this framework, what exactly are we picturing?
The continuous is the realm of waves, fields, smooth, unbroken shapes. Think of a perfectly smooth, endless ocean, or the subtle gradients in a sunset. It's about unbroken wholeness. In mathematics, it's calculus, differential equations, and topology. Now, topology might sound a bit intimidating, but it's basically the study of shapes and spaces that don't change even if you stretch or bend them, as long as you don't tear them. Think of a coffee mug and a donut topologically. They're the same because you can smoothly deform one into the other. It's pretty cool. So the continuous represents connection, context, and a kind of binding force. It's that wave-like, spread out, contextual background field of possibilities.
Okay, connection, context, possibilities. So what about the discrete side of this pairing?
The discrete, by contrast, is the realm of particles, counts, individual entities, distinct states like individual grains of sand, or the distinct clicks of a Geiger counter. It's about intensity, locality, decomposition. It's a definite, localized, and present state, often seeming to stand out from that continuous background. Think of it as the sharp, distinct points or events within that fluid, continuous field.
Right. So this framework then suggests that a true dialectical pairing isn't just any old binary opposition like on, off, or 10. Instead, it's a binary system that embodies the specific, fundamental tension and interplay between discrete and continuous. You call this a brilliant filter. Can you give us a quick, simple example, maybe outside of quantum physics, where this kind of discrete continuous tension creates something uniquely interesting?
Absolutely. That's a great way to think about it. Think about music, for instance. You have discrete notes. C, G, A, each a distinct separate event. That's the discrete part. But then you have the continuous melody, the flow of the sound, the rhythm, the harmony, the way those notes blend and interact over time. That's the continuous aspect. The magic of music isn't just the individual notes or just an unbroken drone, it's the dynamic interplay, the dialectic between those discrete notes and the continuous flow that makes it beautiful and meaningful. That's the brilliant filter in action. It highlights systems where this deep inherent tension is the source of complexity and insight.
That's a great analogy. It really clarifies it. So, okay, if we apply this filter back to our original quantum puzzle, how does it help us understand waste-particle duality better? Does it make it less of a, paradox?
This is precisely where it becomes incredibly powerful, I think. Wave-particle duality isn't a paradox. It's a dialectic. The two aspects aren't mutually exclusive in some unresolvable way. They're in a dynamic relationship. They need each other. The particle aspect aligns beautifully with the discrete. It's that which binds a localized, discrete event, that distinct click in a detector, a specific measurement outcome. It's the moment of collapse, of definition, of becoming something definite. And the wave aspect aligns with the continuous. It's that which decomposes the wave function. This wave function is a continuous field of potentiality, a superposition of states. Think of superposition like maybe like a ghost in a haunted house. It's everywhere and nowhere specific, potentially in many places at once, until you shine a flashlight on it, make a measurement. The wave represents connection, context, and all that's possible before a measurement forces it to pick just one specific result.
So the quantum state isn't simply one or the other. It's this dynamic, context-dependent interplay between both, constantly in flux. It's the relationship.
Precisely. It is the relationship. And the measurement process itself acts as the dialectical engine. Imagine it like a conversation. The continuous wave, our initial idea or thesis, meets the interaction of a detector, the challenging counter idea or antithesis. Through that interaction, that friction, the wave collapses into a discrete particle, and you arrive at a new, more refined understanding of reality, the synthesis. It's this continuous process of definition and redefinition happening constantly.
It's really quite astonishing how this understanding can bridge something as abstract as philosophy with something as concrete as what happens when we observe a particle. And this rethinking of duality, and even something as basic as location, it leads to some truly groundbreaking ideas. What happens when we apply this dialectical thinking to something like defining where something is? Does location itself change?
That's a fantastic question. Yeah, this framework leads to a system of location that isn't about fixed points, but about dynamic interaction. In this view, location isn't just absolute coordinates, that's the discrete aspect, the pin on the map. True location is defined by its context, its relationship to everything else in the continuous field. The map itself, we can think of it in layers. Layer 1 is topology, which defines that continuous contextual space. It's where the particle can be, the entire map of possibilities. Layer 2 is particle decomposition, which defines the discrete, intensive event, is where the particle is measured, the specific pin on that map. So real location is the dynamic interaction between these layers. The map, the continuous context, and the pinned point, the discrete particle event. They define each other.
And this way of thinking leads us directly to the idea of a quantum topological speculative decoder, or QTSD. It sounds incredibly advanced, almost science fiction. But what exactly is this theoretical instrument, and how does it leverage this deep dialectical understanding we've been discussing?
Right, the QTSD. It is envisioned as a decoder that operates on these two intertwined levels we've just discussed, the discrete and the continuous. Its primary function is to decode information within quantum states, those discrete particles or rays that are constantly undergoing decoherence and decay. Decoherence is basically when a quantum system loses its quantum weirdness, its properties, as it interacts with its environment. It loses its ghost-like superposition and becomes more classical, more definite. But crucially, the QTSB doesn't just look at the decay of individual bits. It also decodes the health and integrity of the topological structure itself, that continuous context that's supposed to protect the information.
Ah, okay. So it's not just checking for individual errors like a flipped bit, but also checking the overall health of the quantum environment, the protective field. How does it manage to measure both sides of this coin?
Exactly. On the discrete axis, it measures the rate at which individual quantum bits or qubits lose their coherence or flip states because of environmental interaction noise. Okay. This is like detecting localized errors where particle-like information gets corrupted with the decomposition to classical noise. It's observing the specific moments when information is lost from individual elements. And then simultaneously, on the continuous axis, it measures the protective capacity, the resilience of the overall topological medium. This isn't about individual particles, but global properties. Things like the stability of the energy gap, that's a protective energy barrier in these topological materials. Also, the rigidity of the topological order itself, which is a type of quantum order that makes information robust against local disturbances, local errors, and even the integrity of things called quantum braids. These are like the world lines of exotic, almost two-dimensional particles called anynes. Their paths can literally intertwine and hold information in their patterns, making it extremely difficult to lose. So the QTSD uses what we could call topological tomography to probe this context itself, like taking an X-ray of the entire protective structure, not just looking at the individual bricks.
Wow, okay. And the speculative part of its name, what makes it speculative? Does it predict the future?
In a way, yes. This decoder doesn't just react to what's happening right now. It anticipates. It's designed to run continuous simulations. It uses the measured decay rate of those discrete particles to predict the future load on the system, how much error is likely coming. At the same time, it uses the measured strength of the continuous topological protection to predict the future capacity of the system to handle that load. By synthesizing these two streams of information, the discrete decay and the continuous protection, it can speculate on the future fidelity of the quantum information. So, effectively, it acts as a predictive maintenance system for quantum computers. It aims to foresee potential issues before they become critical failures.
So, in essence, the QTSD perfectly embodies this dialectical structure we've been talking about. It's not just a philosophical idea anymore, but potentially a real engineering application.
Precisely. It captures that fundamental tension right at its core. Its thesis is the continuous binding the topological structure, actively striving to protect information globally, holding it together. Its antithesis is discrete decomposition, the external environment interfering through those localized discrete events, causing decay, pulling it apart. The synthesis, then, is the decoder's output. A real-time assessment of this dynamic balance. It's constantly asking, given the current rate of these discrete attacks, is the continuous defense still sufficient to maintain integrity? It's really a profound extension of deep philosophical insight into potentially practical engineering.
Wow. We've certainly journeyed a long way today from a baffling scientific observation about light and electrons through a sophisticated philosophical framework and then landing on this truly visionary technological concept. It really shows you how fundamental questions about the nature of reality can lead to extraordinary and potentially useful ideas.
Absolutely. And if we connect this to the bigger picture, the QTSD isn't just a decoder of data or quantum states. You could say it's a decoder of reality itself, at least within its domain. It interprets that ongoing dialectic between the continuous and the discrete, providing a model for understanding stability and decay, not as separate phenomena, but as two inextricably linked sides of a single quantum coin. It's like a system designed to understand the very dance between possibility and actuality.
So what does this all mean for you listening in? Well, it means that understanding the universe at its most fundamental level isn't just about putting things in neat boxes or labels. It's about appreciating the dynamic interplay of seemingly opposing forces. Next time you think about something as simple as a location, maybe consider this. Is it just a single fixed point? Or is it a point dynamically defined by an entire continuous context, the map and the pin? And maybe ask yourself, what other non-trivial dialectical pairings might exist in your own world, in your own thinking, waiting to be discovered? Where else is the tension between the discrete and continuous creating profound meaning or surprising solutions? We really hope this deep dive has given you some truly fascinating insights today and perhaps even inspired some new ways of thinking about the world around you. Keep exploring, keep questioning, and keep expanding your understanding.